In this video, we're going to find the shortest distance between two lines in 3D space. So let's say you've got a line 1 here. So this is your line 1. So this is your line 1. It's given by this. So when you read this, this will be your starting position. So line 1 here, your starting position would be, let's just say it's here. So this bit is here. And then this will be your direction. So when time equals, let's say 3, it would be you doing this. So let's just say this vector here is this one here. It would be you moving 1, 2, 3. When time equals 3, it would take you to this point. Okay, so line 2, your second line is this line here, and it's given by this. So when you read this, it will be your starting position is here, and then this will be your direction, your vector direction here. So when this is 4, let's just say it's 4. When s is 4, it would be 1, 2, 3, 4. It would take you to here. So our aim is to find out the shortest distance that exists between two lines. Now in 3D space, the shortest distance might not be around here because it's hard to illustrate this on 2D. But in 3D, the shortest distance could be over here, and the shortest distance could even be like this. It's just because it's in 3D space. It's hard to illustrate it on a flat 2D on your flat 2D screen. So it might not, the shortest distance might not be around here. It could even be something like this. This might be the shortest distance, or this might be the shortest distance. Because it's hard to illustrate on 3D, so it could be like this. Well, anyway, to find out the shortest distance, we would set up a general point on one line. Let's just call it P, and then we would set up another general point on the other line. And the shortest distance exists when this is 90 degrees. When this is 90 degrees. So the shortest distance that exists between two lines is when the vector from P to Q. So the shortest distance exists when the vector here dots it with this direction here, which is this thing here. Let me think. Yeah. So dot it. So to find out the shortest distance, you would demand that this to be 90 degrees, and the way you would do that is to demand that the dot product equals 0, and then the shortest distance exists when this is 90 degrees and this is also 90 degrees. So you would also demand that the vector PQ dot it with this vector here, to be 0 as well. So you would make these two demands. You would make these two demands here. Bear with me. So in order to find the shortest distance, you would need to make these two demands. But the first step is to find out the vector PQ. So I will guide you through this. But our next step is to find out the vector PQ because we need this. So the next step is to find out the vector PQ. So let's look at line 1 and line 2. So let's translate this into x, y, and z coordinates. So translate it into this, and this thing translates it into this. Because if you look at this, so if you look at it in the x direction, it will be this. So you start at 1, and then you add 1s, and then let's look at this one here. And I'll look at it in the y direction. So we are looking at line 2 at the moment. So line 2, you start at 0, and then you add 1s. So now let's look at, looking at line 2, looking at the z direction, it will be you starting at -1, and then you add 3s. So you can always translate this into this here. And then looking at line 1, you can do the same here. So x direction would be this, would be 1t. It would be 1t. In the y direction, it would be 2. You starting at 2, and then 1 plus 1t plus 1t. So you can always translate it into this and into this. And then now, if you want to know the So for given time, so for given time t, so t represents in a way time, s represents in a way time. So for given time, you know the precise location of this general point. So the point is that if you have this equation here, you know, the point is that if you have this for given time, it will tell you precisely where the position will be. So hang on, let me think. This is line 1 here. This is line 1 here. So for given time, let's say t equals 2, 1, 2. Then you have the ability to work out the x, y, and z coordinates of this particular point. When time equals negative 1, then you have the ability to work out the precise location of this point. The x will be here, or the y will be here, the z will be here. So looking at this thing here for different time, because we want t and s to act independent of each other. So you could t here, and this here is s. So we want t and s to be independent of each other. So looking at line 2, if you let's say s equals 4, so it would be 1, 2, 3, 4. Now you have the ability to work out the location of this point here. Well, in the x direction it will be this, in the y direction it will be this, and so on. So now we know the precise location of this point here for a given time, and we know the precise location for this point here for a given time s. So now we can work out the vector from p to q. So p to q, so the position of p will be given by this. For any given time, you know the position precisely. For any given time s, you know the position precisely. So therefore, you can work out the vector. You can work out the vector to try that will take you from p to q. You can work out this. You can work out this vector here. You can work out this vector here by simply getting this, take away this. So in the x direction, so this is the x, this is the y, this is the z. It will be this, take away this. So that will be this, take away this. And then in the y direction, it will be this, take away this. So that's minus 2 minus t. And then in the z direction, it will be this, take away. It will be this, take away this, which will then give you this. So now we have the vector PQ. So we have this vector here now. I will continue in the next video.